প্রিয় শিক্ষার্থীরা, কেমন আছো তোমরা? আমরা দীর্ঘ এক সপ্তাহ পর আমরা আবার এসেছি তোমাদের সাথে মাস্টার শ্রেণীর ডিফারেনশিয়াল ইন্টিগ্রাল ইকুয়েশনের যে কোর্সটি আছে তার ভলতেরা ইন্টিগ্রাল ইকুয়েশন কাকে বলে এটা আমি তোমাদের সাথে আগে আলোচনা করেছি। বিভিন্ন ধরনের ভলতেরা ইন্টিগ্রাল ইকুয়েশন নিয়েও কথা বলেছি। আজকে আমরা মেইনলি আমাদের ফোকাসটা থাকবে হচ্ছে ভলতেরা ইন্টিগ্রাল ইকুয়েশন সলভ করা। একটা ভলতেরা ইন্টিগ্রাল ইকুয়েশনকে আমরা কিভাবে সলভ করব সেইটা আমরা একটা পার্টিকুলার প্রবলেমকে আমরা আজকে দেখাবো তোমাদের সামনে। তার আগে আমি একটু এই ভলতেরা ইন্টিগ্রাল ইকুয়েশনটা নিয়ে কথা বলতে চাই। আমি যদি একটা ইকুয়েশন বোর্ডের মধ্যে লিখতে চাই জেনারেল টাইপস অফ ভলতেরা ইন্টিগ্রাল ইকুয়েশন, তাহলে ইকুয়েশনটা এরকম হবে সম্ভবত। সেটা হচ্ছে হলো আলফা এক্স, আমাদের টপিক হচ্ছে ভলতেরা integral equations, integral equation। শিক্ষার্থীরা, আমরা যেটা বলছিলাম যে ইন্টিগ্রালে ভলতেরা ইন্টিগ্রাল ইকুয়েশনের জেনারেল টাইপটা হচ্ছে হলো আলফা এক্স phi of x equals to f of x plus lambda a to x kappa xt phi of t dt. This is the general types of Volta integral equation where the upper limit is variable. This is x and lambda is the parameter. এখানে আমরা কি স্পেশাল কেস নিয়ে আলোচনা করেছিলাম। if alpha x equals to 0, then the equation reduces to f of x equals to minus lambda a to x kappa xt phi t dt. This is the Volterra integral equation of the first kind. Volterra integral equation of the first kind if alpha x equals to 0. Case number 1. If alpha x equals to 1 and phi of x equals to alpha x equals to 1, if alpha x equals to 1, then phi of x equals to f of x plus lambda a to x kappa xt phi t dt. This is the Volterra integral equation of the second kind. This is the first kind. It was first kind, and this is the Volterra integral equation of the second kind. We discussed this earlier. Phi of x equals to f of x plus lambda a to x kappa xt phi t dt. Volterra integration of the second kind. And third case was if alpha x equals to 1 and f of x equals to 0. Alpha x equals to 1, f of x equals to 0, then we have f of x equals to 0, then phi of x equals to lambda a to x kappa xt phi t dt. This is called the Volterra integral equation of the second kind. Homogeneous Volterra integral equation of the second kind. This is homogeneous. It is homogeneous. Homogeneous Volterra integral equation of the second kind. This is the first kind, the second kind, and this is homogeneous. There are three types of Volterra integral equation. Now we'll discuss an important theorem. The theorem is this is theorem. A Volterra integral equation VIE আমি সংক্ষেপে লিখেছি of second kind, a Volterra integral equation of second kind phi of x equals to f of x plus lambda a to x kappa x t phi t dt. A Volterra integral equation of second kind, phi of x equals to f of x lambda. ওকে, এখানে আমরা যদি লিমিটটাকে ফিক্সড করে দিই 0 to x কাপ্পা x t না বলে আমি এখানে কাপ্পা x যাই ইউজ করছি, আর তাহলে এখানেও আমার phi of যাই, আর এখানে তাহলে আমার d যাই হবে। এত has only, very important thing, only one solution, has only one and one solution, one and only one solution, has only one and one solution given by the formula R x xi lambda equals to kappa x xi plus v equals to 1 to infinity lambda to the power v kappa v x xi converges for all values of lambda. That means if phi of x equals to f of x plus fx lambda 0 to x kappa x xi phi xi d xi, if this is a Volterra integral equation of second kind, then it has only one solution. R x xi lambda equals to kappa x xi plus v 1 to infinity lambda to the power v kappa v x xi, and this series is converges for all values of lambda. And this is very important thing. This series is known as Neumann series. V 1 to infinity lambda to the power v kappa v x xi. This is known as Neumann series. আমরা আগে বলেছিলাম যে আমরা আজকে একটা ভোল্টেরা ইন্টিগ্রাল ইকুয়েশন সলভ করব। আমি একটু তোমাদের রিকল করে আসলাম পিছন থেকে যে ভোল্টেরা ইন্টিগ্রাল ইকুয়েশন ফার্স্ট কাইন্ড, সেকেন্ড কাইন্ড এন্ড হোমোজেনাস ইকুয়েশনের চেহারাটা দেখালাম, এবং তার সলিউশনটা আমাদের কি হবে r x xi lambda. This is resolvent kernel. ওকে, আমরা প্রবলেমে যাচ্ছি। Solve xt equals to e to the power minus t plus 0 to t, upper limit variable, lower limit fixed, that is 0 to t, e to the power minus t minus s x s ds. This is Volterra integral equation. Xt equals to e to the power minus t, that means it is small ft, and lower limit a equals to 0, upper limit x equals to t, which is a variable, and phi of t will be minus t minus s xs ds. Solution. We know that the solution of the Volterra integral equation xt equals to f of t plus lambda a to t kappa ts xs ds is, so this is equation number 1. This is equation number 1, and this is equation number 1. This is equation number 1, and this is equation number 2 is xt equal to function of t plus lambda a to t r t s lambda function of s ds, equation number 3. Solution of the Volterra integral equation x2 equals to f of t plus lambda a to t kappa ts xs ds. If this is the external Volterra integral equation, then the solution will be xt equal to f of t plus lambda a to t r t s lambda f of s ds, which is the kernel, the resultant kernel বলছি আমরা এটাকে। Comparing 2 with 1, comparing 2 with 1, we will get lambda equals to 1, function of t equals to e to the power minus t, function of t equals to e to the power minus t, lambda equals to 1, and kappa ts, this is kappa ts, kappa ts equals to e to the power minus t minus s, and lower limit a equals to 0, lower limit a equals to 0. So we can write down f of s equals to e to the power minus s. Since f of t equals to e to the power minus t, so we can write down f of s equals to e to the power minus s. Also, we have the resolvent kernel. We have discussed this earlier. We have resolvent kernel RTS lambda, resolvent kernel RTS lambda equals to n 1 to infinity lambda to the power n minus 1 kappa n ts. একটু আগে আমি যেটাকে v দিয়ে লিখেছিলাম n 1 to infinity lambda to the power n minus 1 kappa n ts. This is the resolvent kernel RTS lambda. So this is equation number 4, resolvent kernel equation number 4, and kappa n ts equals to s to t kappa tu kappa n minus 1 u comma s du, n greater or equals to 2. So this is equation number 5. Kn, k is the suffix, kn ts equals to s to t kappa t u kn minus 1 us du, and greater or equals to 2. And also kappa 1 ts, also kappa 1 ts equals to kappa ts. That means e to the power minus t minus s. This is equation number 6. Equation number 6. For n equals to 2, from this equation, equation number 5, kappa 2 Ts will be S2T, kappa T U, kappa T U into kappa n equals to 2, 2 minus 1, 1, kappa 1 U comma S du. That means kappa 2 equals to S2T, kappa Tu means e to the power minus t minus u, kappa tu e to the power minus t minus u, and kappa 1 us equals to e to the power minus us u minus s. That means u minus s du. আবার বলছি, kappa tu is to the power minus t minus u, and kappa 1 equals to kappa ts, that means e to the power t এর জায়গায় আমার এখানে u বসাতে হবে, s এর জায়গায় s, তার মানে u minus s du। এখান থেকে আমরা kappa 2 এর মানটাকে আমরা বের করে ফেলতে পারবো। তাহলে কত আসছে এখান থেকে? আমি এটাকে লিখতে পারি ইন্টিগ্রেশন ওভার s to t e to the power minus t plus u minus u plus s du, integration over s to t e to the power minus t minus s du। আমরা উপরে চলে আসি, that means kappa 2 ts, kappa 2 ts equals to হচ্ছে তাহলে আমরা যদি ইন্টিগ্রেশন করি in aspect of u e to the power minus t minus s, it is a constant, that means with respect to u t minus s is constant, integration of e to the power x equals to e to the power x, that means constant will be outside, minus t minus u, and integration of du means u upper limit t lower limit s, that means e to the power minus t minus u into t minus s, that means kappa 2 ts equal to t minus s equal to e to the power minus t minus u, kappa 2. Now putting the value of n equals to 3, again putting the value of n equals to 3, let's say this is equation number 7, last 6, this is equation number 7. For n equal to 3, kappa 3 ts, for n equals to 3 in resolving kernel, kappa 3 ts, it will be s to t kappa tu and kn minus 1, that means if value of n equals to 3, then kappa n minus 1 means 3 minus 1 equals to 2, kappa 2 us du, that means integration over s to t, kappa tu means kappa tu, আমি লিখে রাখি kappa tu equals to হচ্ছে হলো e to the power minus t minus u, তাহলে e to the power minus t minus u, আর kappa 2 us, kappa 2 us from here e to the power u minus s into e to the power minus u minus s du, because kappa 2 ts kappa 2 us, putting the value of putting u in the place of t. The place of t. So this will be u minus s integration over s to t, u minus s into e to the power minus t plus u minus u plus s du. That means integration over s to t, u minus s e to the power minus t minus s with respect to u. Now in respect of u, e to the power minus t minus s is constant, and e to the power u minus s e to the power, that means kappa 3 ts equals to e to the power minus t minus s. If we integrate u minus s with respect to u, then it will be u minus s whole square by 2, upper limit t, lower limit s. ওকে, আমি একবার ইন্টিগ্রেশনটা করে ফেলেছি। e to the power minus t minus s কে আমি আউটসাইডে নিয়ে আসলাম, আর u minus s কে ইন্টিগ্রেশন করলে u minus s whole square by 2, and so it will be equal to e to the power minus t minus s, e to the power minus t minus s, it is the value of u, তার মানে t minus s by 2 whole square, it was equals to 0, while limit 0 to s, it will be 0 to s, means it will be e to the power minus t minus s into t minus s whole square by 2 minus 0. That means t minus s whole square 2, we can write down it factorial 2 factorial into e to the power minus t minus s. So this is equation number 8. That means kappa 3 ts equals to t minus s whole square by 2 factorial e to the power minus t minus u, e to the power minus t minus s, e to the power t minus s, kappa 3. Okay, similarly আমি আর করতে যাচ্ছি না, similarly n equal to 4, তাহলে kappa 4 ts will be t minus s whole cube by 3 factorial e to the power minus t minus s. So this is equation number 9. সিমিলার ওয়েতে যদি আমি n equals to 4 বসিয়ে এটাকে আমি ইন্টিগ্রেশন করি, তাহলে আমি সেখান থেকে kappa 4 টাকে পেয়ে যাব। ওকে, kappa 4, we can assume that kappa n ts equals to t minus s whole to the power n by n factorial, n minus 1 factorial, because for 4 3 factorial, for n minus 1 factorial, e to the power minus t minus s. So this is equation number 10. Then for n plus 1 instead of n, from 6 gives kappa n plus 1 ts equals to s to t kappa tu kappa nus du. Kappa nts equals to 6 নম্বর সমীকরণ থেকে s to t kappa tu. That means we want to prove this by method of induction. You know the procedure of method of induction. For n equals to 1, n equals to 2, n equals to 3, then you assume that it's true for n equals to n plus 1. Then you can say that this theorem or this problem is true for all values of n. This is the procedure. So we can write down kappa n plus 1 ts equals to s to t e to the power minus t minus u minus s whole to the power n minus 1 by n minus 1 factorial e to the power minus u minus s by 6 and 10 kappa n ts kappa n us kappa n us তাহলে kappa n ts এর জায়গায় আমি যদি kappa n us বের করতে চাই তাহলে আমি এটা পেয়ে যাব integration over du. Similar way, if we integrate this, we will get the value of, I am skipping some line, we will do this in the same way. We will get t minus s whole to the power n by n factorial e to the power minus t minus s. Same way, আমরা যদি এটাকে বাইরে নিয়ে আসি ফ্যাক্টরিয়াল করে তাহলে আমরা t minus s whole to the power n by n factorial e to the power t minus s পেয়ে যাব। তাহলে this is equation number 11. Thus, by mathematical induction, this is a procedure. Mathematical induction 5 holds for all positive integer n greater or equals to 2. The theorem holds for all positive values of n, and n is greater than or equals to 2. Now from 6 we can write down r t s lambda equals to 1, n equals to 1 to infinity kappa n ts, since lambda equals to 1. That means write down each kappa 1 ts, kappa 2 ts, kappa 3 ts, kappa n plus 1, kappa n plus 1 ts up to infinity. This is an infinite series. Now putting the value of kappa 1, kappa 2, kappa 3, kappa 4, kappa n plus 1. Now putting the value of kappa 1, kappa 2, kappa 3, kappa 4 up to kappa n plus 1, we will get the result e to the power minus t minus s plus t minus s e to the power minus t minus s plus t minus s whole square by 2 factorial e to the power minus t minus s plus t minus s whole cube by 3 factorial e to the power minus t minus s up to kappa n plus 1 is equals to t minus s whole to the power n by n factorial e to the power minus t minus s to infinity. That means to the power minus t minus s into e to the power t minus s, because e to the power x equals to, we know the formula, e to the power x equals to 1 plus x by factorial 1 plus x square by factorial 2. We know the formula, e to the power x equals to 1 plus x by factorial 1 x square by 2 factorial x cubed by 3 factorial. If we take it common, e to the power minus t minus s, then it will be 1 plus x. Okay, I can write down another line. That means e to the power minus t minus s 1 plus t minus s by factorial 1 t minus s whole square by 2 factorial t minus x whole cube by 3 factorial. Well, the infinite series. That means e to the power minus t minus s into e to the power t minus s, that means e to the power 0 equals to 1. That means resultant kernel is 1. Now putting function of t equal to e to the power minus t, a equals to 0, and resultant kernel t s lambda equal to 1, lambda equals to 1, f of s equals to e to the power minus s in equation number 3, which was the solution was, we will get xt equals to e to the power minus t plus 0 to t 1 into e to the power minus s ds. That means e to the power minus t plus e to the power minus s by minus 1, upper limit t, lower limit 0. That means e to the power minus t minus e to the power minus t and plus 1 equals to 1. Thus the required solution is, xt equals to 1. Okay, dear friends, আমরা আজকে এখানে শেষ করতে চাই। আমরা পরবর্তী ক্লাসে অন্য কোনো টপিক নিয়ে তোমাদের সামনে হাজির হব। ধন্যবাদ সবাইকে।